Let's take a look at one more example. It's a little bit harder. We have a transformation T that maps R2 into R3. This is a linear transformation such that the transformation on -3, we know the transformation on -3, -3, and we are given the transformation on 2, -1. We need to find the standard matrix A of T. We know a standard matrix A exists because every linear transformation of this form has a standard matrix. Okay? In this case, A is going to be a 3×2 matrix. In order for the matrix to make sense, it has to be 3×2 because it needs, the input has to be two-dimensional vectors, so 2×1 vectors. So if we're going to left multiply it by a matrix, it needs to have two columns. The matrix needs to have two columns. Okay? And if the output needs to be three-dimensional vectors, so that'd be a 3×1, the rows of matrix A, I need to have 3 rows in order for this to make sense. So it's going to be a 3×2 matrix. Okay? The columns of a standard matrix, we know, are just the transformation on the vectors in the standard basis of the domain. For R2, which is our domain, the standard basis are vectors I and j. So I just need to find the transformation on vector I. I need to find the transformation on vector j. If I could find those, then I have my standard matrix A. Okay? So how do I actually find that? I know the transformation of these two vectors, -3, -3, and 2, -1. I'm not given right away the transformation on vectors I and j. So what we're going to do is we're going to use the properties of linear transformations to find the transformation on vector I, the transformation on vector j, by expressing I and j as linear combinations of the vectors we do know about. So let's start with vector I. Okay? Vector I, so vector I is the vector 1, 0, right, in 2D, in R2. Now we want to see if we can express vector I as a linear combination of these two vectors. So that is some constant times our first vector, -3, -3, plus some constant A2 times our second vector, which was 2, -1. Okay? We want to see if we can find A1 and A2. Now we've done this enough that we should recognize, oh, okay, this is just solving a system of linear equations. We can put this system into augmented matrix form. The columns in the coefficient matrix, when in augmented matrix form, are just the columns of the linear combination. So -3, -3, 2, -1. The augmented part is what the linear combination equals, which in this case is 1, 0. If I could get this into reduced row echelon form, I could find the solution to the system. That'll give me A1 and A2. Okay? So I don't want to call this matrix A, so let's call it M. I don't want to call it A, by the way, because I already have a matrix A, right? So M is going to be the matrix with the first row, -3, 2, 1. The second row, -3, -1, 0. And I want to find the reduced row echelon form of matrix M. And there it is. We get 1, 0, -1/9, 0, 1, 1/3. The last column is the augmented part, and we can immediately see we do have a solution. We have a unique solution, and the coefficients of our solution, 1A1 equals -1/9. 1A2 equals 1/3. Okay? So that means I is equal to negative 1/9 times my first vector, which is negative 3, plus my second coefficient 1/3 times my second vector, which is 2, -1. So now I'm going to take the transformation of this. Transformation of vector I is just the transformation of my linear combination. By the properties of linear combinations, I know that I could split this into two transformations over addition, and then I could pull out the scalar. So if I apply those two operations, which I can do with linear transformations, I'm going to get negative 1/9 times the transformation of vector negative 3, I'm going to get 1/3 times the transformation of 2, -1. And this is the whole purpose of why we're doing this, because I actually know the transformation of negative 3. I know what the transformation of 2, -1 is. I'm told that at the beginning. The transformation of negative 3 is negative 3, 9, -3. So I'm going to get negative 1/9 times negative 3, 9, -3. Plus 1/3. And now times the transformation of 2, -1. The transformation of 2, -1 is 5, 3, -7. And so if I just do the arithmetic, I will be able to find the transformation. Negative 1/9 times negative 3 is positive 1/3. Plus 5/3 is going to be 6/3. That's 2. Negative 1/9 times 9 is negative 1. 1/3 times 3 is 1. Negative 1 plus 1 is 0. Negative 1/9 times negative 3 is positive 1/3. Minus 7/3. Positive 1/3 minus 7/3 is negative 6/3. That's going to be negative 2. Okay? So that's the transformation on vector I. And so that's going to be the first column of my standard matrix A. Okay? We've got to do all that one more time to find the second column for the transformation on standard matrix J. So now let's do the same thing, but for vector J. We want to express vector J as a linear combination of the two vectors I do know the transformation of. Negative 3, and 2, -1. Okay? So vector J is vector 0, 1. So I want this to be equal to some constant times the first vector I know the transformation of, negative 3, plus some constant b2 times the second vector I know the transformation of, 2, -1. Okay? Again, this is a linear system of equations. I can solve this by converting it to augmented matrix form and getting it into reduced row echelon form. The first column is negative 3, the second column is 2, -1, and the augmented part on the other side of the equal sign is 0, 1. Okay? Notice that's almost the same matrix that I had before. So rather than retyping all this in, I'm just going to copy this, paste it into a new code box, and I'm just going to swap the 1 and the 0 in the last column. So instead of 1, 0, I get 0, 1. Now this matrix matches this matrix. If I find the reduced row echelon form, there I get it. Okay? The reduced row echelon form of the matrix is 1, 0, -2/9, 0, 1, -1/3. which means my first coefficient b1 is equal to negative 2/9, and my second coefficient b2 is equal to negative 1/3. So vector j is going to equal to my first coefficient, negative 2/9, times my first vector, which was negative 3, plus my second coefficient, which is negative 1/3, times my second vector, which was 2, negative 1. So I want the transformation on j, which means I want the transformation on this linear combination. Because it's a linear transformation, I could split up the transformation over addition, pull out the scalars. Remember, linear combinations are preserved under linear transformations. Okay. The transformation on negative 3, if you go back to the original problem, the transformation was the vector negative 3, 9, negative 3. And the transformation on 2, negative 1, again, you have to go back to the original problem. It tells us the transformation was 5, 3, negative 7. And so by just doing the matrix arithmetic, or the vector arithmetic, I get the transformation on j. So negative 2/3 times negative 3 is going to be negative 2/9 times negative 3 is positive 2/3, plus negative 5/3 is going to be negative 3/3, that's going to be negative 1. Second component, negative 2/9 times 9 is negative 2. Negative 1/3 times 3 is negative 1. Negative 2 plus negative 1 is negative 3. And finally, negative 2/9 times negative 3 is positive 2/3. Negative 1/3 times negative 7 is positive 7/3. So 2/3 plus 7/3 is 9/3, or 3. And now I have the transformation on vector j. Okay, so I've got the transformation on I, I've got the transformation on j. Those mean that I have the columns for my standard matrix. So matrix A is going to be, let's see, the first column is the transformation on I, which was 2, 0, negative 2. That was the transformation on my first vector in the standard basis I. So the first column of A is 2, 0, negative 2. And the second column in A is the transformation on vector j, which is negative 1, negative 3, 3. And that's my answer. That is the standard matrix of the transformation. And so, in fact, with just the transformation on those two vectors, I was able to find the transformation on any vector x. All I need to do is take a vector x in R2, and if I multiply it on the left by matrix A, I will get how that vector is transformed.